Example 1.c.2. Given. Pin P is constrained to move in the slotted guides that move at right angles to one another. At the instant shown, guide A moves to the right with a speed of VA, a speed that is changing at a rate of V dot A. At the same time, B is moving downward with a speed of VB, with a rate of change of speed V dot B. So we're given VA is equal to 0.2 meters per second, VB is equal to 0.15 meters per second, V dot A is equal to 0.75 meters per second squared, and V dot B is 0. And we need to find the rate change of speed of P and the radius of curvature of P. If we put down the units here, I hat, J hat. B is moving in the negative direction, VB, in the negative J direction, and VA in the positive I direction. So for the rate change of speed of V, we need V dot, which is found in the equation, the vector equation for path. V is equal to V dot E sub T hat. Can rearrange this for E sub T hat is equal to the vector V divided by rate change of speed V. We need to start with our givens, so we use the Cartesian vector equation, VA I hat minus VB, because VB is negative in the J direction. We can find the these are not dots. That's my mistake, but we can find the magnitude of V with the square root of the squares of VA and VB. This negative doesn't matter because this is squared, turns into a positive. So then we have E sub T. If we use this and plug it in, we get VA divided by VA squared plus VB squared I hat plus VB over the square root of squares again. And we know that V dot is equal to the acceleration vector. So acceleration vector dot E sub T hat, which gives us the final equation, V dot A times VA plus V dot B times VB over square root of the squares again. We just combined the fraction, skipped a few steps to save time. Then when we plug this in, V dot A is equal to 0.75 meters per second squared times VA, which is 0.2 meters per second. And then this VB dot times VB is 0, because VB dot is 0. So divide that all by 0.2 squared plus 0.15 squared. That is equal to 0.6 meters per second squared. So there is our answer for the rate change of speed. Now to find radius of curvature, we're going to write both of the vector equations in path and Cartesian for acceleration, which are v dot a I hat plus v dot b j hat, and this is still 0, but I'll write it anyway. And then for path, it's the rate change of speed, e sub t hat, plus v squared over rho, e sub n hat. And then, so we need to turn this vector equation into some scalars that we can use in the equations. So if we take the magnitude, which is a scalar, we can find it using square root of squares, which is just v dot a squared because this is still 0. So this stays 0.75 meters per second squared. And then if we write the other side of this with the absolute value being equal to the magnitude, get v dot squared plus v squared over rho all squared is equal to the magnitude. Since we have the magnitude and we have the rate change of speed and we have the velocity, we can put this equation in terms of p, or rate change of speed, rho I mean, not p. So we can do the magnitude squared is equal to rate change of speed squared plus v squared over rho all squared. And we can just plug in the numbers we have. I don't think we actually wrote down what this is equal to. We can do that real quick. The 0.25 meters per second. And then we have everything we need. 0.25 squared. Our rate change of speed was 0.6 squared. And our acceleration is 0.75 squared. And this comes out to 0.138 repeating meters. And that is the radius of curvature.